Okay, so are we back? We all are in the same page now. We all have done the first P analysis. Is there any problem with the first P? So I wanted to go a little faster, but someone said that maybe we need to focus on some parameters also. So in the first P, the parameters we used, those are okay, and I set some of the parameters, but there are lots of other things we can do. So if we just write first P or any command for any tool and then write the help dash dash help, or we can write sometimes H. And see what does it say for dash dash help. Not in the screen, in your screen. Okay, so for any new tool that we want to use, we can use this help option so that it can tell us that what we can do with the tool. For example, here you can see that we use the dash I option already, the input 1, the dash O, output 1, small letter I and O, and the other thing is caps lock I and O, big letter. Also, if we want to customize the adapter sequence, right? So someone was asking that if we want to provide a adapter sequence that we want to omit it, we want to remove it from our sequences, we can do that also. So for that, you can see here lots of parameter we can use, but for the adapter part, you can see that the adapter দিলে এখানে আসবে না। So we can provide here the adapter sequence _ R2. So maybe after writing this parameter, that dash dash adapter sequence R2, then we can provide the sequence. Or for R1, we can also do by using the adapter sequence. Then we can also trim by quality score. For example, here we can remove the poly A tail or anything poly A or poly T by providing the length. Then we also can do the quality check and remove the part that we do not need by these options like cut right window size, cut right mean quality. There are many options we can do. That's why first P actually came out as a good one, because it has, it allows us to do many parameters. Space there, you will put space, then the value, and then again the space and another parameter. For example, for the JSON and HTML, we provided the name of the file, the output file. Also, for like cut by quality 5, cut by quality 3, we can just for any tool to be happy with the Linux environment or using the tool, you just provide you see the manual and provide or use that help option. And it's very easy to get what it can do to get the parameters. And I think if you at least try with these sequence and with these two tools, first QC and first P, you will be able to learn many things to move around in the Ubuntu or Linux environment, because it has many interesting results you can see. Okay, so our first two thing was analyzing the quality and then trimming the data according to the quality. I mean, whether we need a filtering or whether we need to cut the first front and later part, or maybe we need to filter it for the adapter sequence or primer sequence, etc. Okay, so before the break, we were trying to send our this folder, the first Q analysis folder, to our HPC account of all of our account, so individual. So how many of you were successful in doing so? Okay, so those of you who could not track, maybe we can write the command again. It is SCP, secure copy, then dash small r. I made a mistake earlier that it was not bigger, it's a smaller. Then the name of the folder that you are trying, that is first Q analysis. This is the name of the folder that I'm trying to send to my HPC account. Then I will write down the address of my server, which is the username @ awens.osc.edu, then a colon. See the format, it's a colon, then address of the folder, which is users, what was it, PG? Can anyone tell me the number? PGS 099. 0299. Okay. Okay, then the username, and do not forget to write the slash after the name, folder name. And now if I press enter, it is asking me for password. So I will write down the password. And if everything is okay, it is now transferring the files in my folder to the HPC account. And it is now showing the details that what percentage is uploading there. So now this file, this folder has many sequences, right? We have the first QC reports, we have the first P reports. So there are many files now in the folder. And we can also see the what is the size of the file. It is actually not scrolled up. I mean, whatever it is transferring, it is now showing there. So it had the 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 or 11 files. And all of this is now transferred to my HPC account. So if I want to do the mapping or the assembly in that HPC, then I will need to upload my files from here. Or in any case, sometimes we need to upload the files in server. So this is the way we can do it. Any question? Okay, so there is another tool that is called multi-QC. But I mean, you can use that. You can try using that multi-QC, and which will take multiple file at a once and do the quality analysis. But we will not see that now. Multi-QC can be used if you want. We will proceed to mapping. How do we map the reads to the genome, the reference mapping? So for that, apart from the 2 reads we have, what else we will need? What else can we need apart from the reads? We will, key data? We will need a reference data, good. So we will need a reference genome with which we will map it, map the 2 reads we had. Okay, don't need this, getting the genome. So the genome is actually, we will take the E. coli genome. E. coli is a bacteria, and we will get, I mean, we got this genome from the NCBI database, genome sequence. Its name is GCF something. So in the Slack channel, the course material channel of Slack, you can find it, the GCF something.fna. It's the reference genome, and it's the E. coli genome that with which we are going to map. So can everyone download this? And can everyone transfer this file to the HPC? the reference file also? Okay. So what we were doing it in organized way. So we created a directory called first QC analysis. Now we will create a directory that is named as mapping. So this is the third step actually. For QC and the trimming part, we use the same folder. Now for the mapping part, we are trying to use a different folder. and first we will, it's in my computer. So first we will transfer the reference genome in this folder. So we will need to have the reference genome here. So if we have this in the download folder, right? When you download it from internet or anywhere, it normally goes to the download folder. So you can write the command that cp means the copy, then a space, then the destination or the address of the folder where the sequence is. So for in my computer, it is in the another folder. It's not in download. It's in so this one is a folder. It will not be the same for you, but maybe your one is in the download folder where you downloaded it. And then you put the space and write down the destination folder name. So the destination folder is the mapping folder that we just created, like this. And then if you press enter, it will transfer the any file you can transfer with the cp command. So the difference between cp and scp is that for remote transfer, we use the scp as a secure copy, but for transferring a file in my own computer, I can use the cp. Do you know the command for cutting one file and moving it to another file, another folder? Move. So the cut option is actually not cd, it's mv, the moving. Okay, so now we all have the genome here. I will just see that ls, sorry, ct my map, right? So like this one, we will have the reference file, and now we will need the reads, which is in which folder? The trimmed reads. The trimmed reads are in the first QC folder, and we will do the reference mapping now. So for mapping, we can if you want, you can gunzip this GZ formatted file, but if it is in not GZIP, you can just keep it in FNA. So we will use the tool named bowtie 2 for mapping. So just at first check whether you have the bowtie. BOWTIE 2, bowtie 2. Just check whether it is in your laptop or not. If it is not there, you can just try sudo apt install for Ubuntu, actually, for install bowtie. And then press enter and it will automatically install the software. I mean, it is easier now in Ubuntu that they keep these softwares in the repository, but otherwise we will need to download it from their website and then sometimes build it, or sometimes there are ready to use bin files that we can use for to use the command. Okay, so the command will be the bowtie 2, then the genome file, the reference file. We will need to index, or this is a reference genome, and we will need to index this file, not this one. Bowtie install. Oh, okay. Okay, so we can wait while it is being installed, but I hope that everyone has the file, the software tool there. And in most of the HPC, in our HPC, the bowtie is also there. So we can see it there also. Let me open another terminal so that I can directly go to the HPC. You can go through your on-demand option, that is, if that is easier for you. Otherwise, we can just go from here through the SSH option. So you can just type SSH, which is a secure shell. If you are comfortable with the on-demand option, that's okay. That's a easy way to access. Otherwise, you can try this way also, that SSH and then your username @ awens.osc.edu. And then it will ask for your password. And now in this terminal, I am now in the login node of the HPC. It scroll correct. When I am zooming this in, that it's getting the problematic. Okay. Well, this is my folder there, and you can see the folder FASTQ analysis right in the bottom here. And these are some of the work that I did earlier. So I can just So do you know that how to check whether a software is installed in our HPC? There is a command called module spider. Spider can show you whether something is available, like bowtie. if I want to see that if bow tie is installed here, I will write module spider bow tie 2. And since it is showing the version that bow tie 2.4.1 is already installed there. So we can use the bow tie from HPC also. If there is, if our computer is not very speedy or not very upgraded, then we can use the HPC also. And actually for, we are now doing it with a small data set. That's why we can do this in our computer, but otherwise it might take a long time in our computer. Okay, so all of us have the mapping folder here, and it has a reference genome. Now what we will do, we will write bow tie 2, and then there is an option like bow tie 2 build, align, what we want to do. It is asking that what we want to do. So at first we will index the reference genome. So for any book, we have the index, na Shuchipatra. So it tells us the table of content that tells us in which section which gene is, or the localization. It can show us the location. So if we say bow tie 2, then build, and then write the GCF or my reference genome, and then press enter. There was some problem. Check the problem. Index করতে ভুলে গেছি. Okay, bow tie 2 build GCF, then oh, okay, we need to write the index file output name. It was actually showed the error here. The format is bow tie 2 build, then options, if any, I want to use any options, then reference in input file jeta reference, and then BT2 index base. The index file that I am creating, I need to provide its name there. So the format is in the 4 section. The first one is the common bow tie 2 build. Then if we want to use any of the options available, then the reference genome name. Don't put that greater than or sign in your actual command. In the manual, they show it like this so that we can understand that this is like a quotation, that we do not use the greater than or smaller than sign. Then BT2 index. So now if we just do it again, bow tie 2 build, then the reference genome name, and then I will just put the same name with a dot FAI. So this will be the FASTA index file. So it will have the FAI option, and we'll press enter then. So it's showing what it is doing. You can see as it goes that এটা আমাদের ইয়ে, মানে এটা ইয়ে না, ম্যাপিং কি বলে এটাকে, এটা HPC না, না HPC তো আমাদের কম্পিউটার. So what we are doing now is in our own computer, right? We are not working in the HPC. Are we all okay? I mean, we transferred the files to HPC, but the bow tie option now we are writing, it's not in the HPC. It's in your own computer. If you are doing it on HPC, then just stop it there and we will do it in our computer. At first, we are doing it in our computer. You can see here that it's my computer name and it's my username. So this is in my computer. So whatever we are doing now, we will do it in our computer. And if we need to go to the HPC, then we will tell and then go. So when we wrote this command that to build the index for this reference genome, it's showing it's showing whatever it is doing. Like what it is doing actually. So it found that the input file is in DNA or FASTA formatted. Then it first created a small index, reading the reference size, calculating the length like this, and then many more things that we might need to see if we need to go into the details. And also it gives some statistics like the length or the size of the genome. And finally, it gives us the FAI file, the index file. And it showed the total time for mirror index was something 3 seconds. Or let's write ls and see what it created. So by writing the command ls, we can see that it created 1, 2, 3, 4, 5, 6 more files with the FAI option and the BT2 option, BOTI2 index option. And there is two file with the reverse option. So it may vary, not necessary that you will have these 6 files only. It can be varied depending on your genome size or your genome location. Okay, so could we all get this data so far? No, it's not doing well in your computer. Is that the problem? Error. It's showing error. Okay. The command for indexing is the BOTI2 build. BOTI2-build. And remember that you are doing it in your own computer. Just do not do it in HPC right now. Okay, we will do it in HPC later. So in your computer, just write BOTI2 build, then the FNA or the reference file name, the FASTA format file. And then the same name, you can put it in same name, or you can just rename it. You can just rename it to GCF something FNA to E. coli FNA, if it is easier for you. You can just rename it and put the same name. The same name will make it easier to handle later. So E. coli.fna.fai. You can do it in this way also. Just 3 components, BOTI2, then the reference genome name, and the output index file you want to have the name. So that thing. So it has 3 segments in this command. Is it working now in your part? What error is showing? Could anyone generated the file? This one? A commenter. BOTI2 build, then the reference name, which is GCF something FNA, and then the index name, which is GCF something FNA.FAI. If you have the file in GZ format, it's okay if you unzip it. Not for the first queue. You do not need to unzip the first queue, but the reference can be a good way to unzip. Have you unzipped it? Okay, you can try this with unzipping. For unzipping, if you have the the command, right? Gunzip. Then the file name something.gz. You can just unzip. If it is on with .gz, you can unzip this with this command. So what we are now trying to do is mapping the two reads we generated, I mean the two paired end reads with the reference genome. And for your information, this is for E. coli reference genome, E. coli genome. ও আচ্ছা, এখানে যেটা ছিল ওটা জিপ করা ছিল না, Slack channel একটা. Okay, in the Slack channel, the file was in gunzip gz file. So better you unzip it with the command g unzip বা gunzip space, then the gcf something, then dot gz যেটা ছিল সেটা. And then try the bow tie. Maybe it will be easier now. Okay, now what we will do is mapping the reads with the reference. So our reads are in the FASTQ analysis folder, right? So at first we will write bow tie 2. Then dash x. Dash x is saying that it is now using the indexed file. So this is the parameter. Then you can see that it's showing the index file's address. So g something dot fna dot fai, not the main file, but the index file. Then I will write dash 1. Dash 1 is my first R1 read. So where it is in the first QC analysis folder, which is in the upper folder, like this. And then we will target the trimmed files. The file that we trimmed already, we will target that one. So after writing dash 1 space, we will write the R1 file. I mean, we will call the R1 file, then dash 2. You are understanding this notation, right? That dot dot dash, it means that it is in a upper folder, upper directory, and then in the FASTQ analysis folder is there. We are now in the mapping folder, and our trimmed files are in the FASTQC analysis folder. So we need to show the software that it is in that folder. So we are writing this address in this way. So dash 2 dot dash, then FASTQ. Okay, so far we have 5 components here. Sorry, 1, 2, 3, 4. 3 components here. So first, the bow tie 2 is the command. Then for dash X, we are saying it that go for the index file. Then -1 means go for the first pair of the reads, that is R1. And then -2, which is the second pair of the read, that is the R2 read. After that, we will show that the output file name. So this will map. So we just say that S. Now I want to give it a good name. I mean, I'm not liking the full name of this. So I'm naming it as ecoli.sam. It's the output file, which will be in SAM format, the sequence alignment map format. So I wrote it as -S, and the name, you can give it any name, but don't forget to give it a reasonable name. Since it's an E. coli reference genome, I wrote it as ecoli.sam. Okay. So are we all in this page? I mean, in so far? Any problem? Pichone karo problem ache? Okay, now just put enter or press enter. Again, make sure that you are in your own computer, not in the HPC. Since it is now doing the mapping, it will take a little time. If we want to see whether it is actually working, we can open another terminal and write down their top. Yes, top will show me what which softwares are running or which process are running in my computer right now. So you can see here that bow tie to align, this option is now running. And it can see, it can show that how much percentage of the CPU is being used. It is 84% now. How much memory is being used and which user. And you know that every job in a computer has a name or ID, which is a PID or the process ID. And there are many more details which you will understand when you explore on your own. So it's still running, because sometimes we may get confused that whether it is actually running or not, because it's not showing any verbose. So we can just check here in the top, like the task manager in Windows. So when it will stop, I can just check that it is a stop and then see the results. It will give you an idea that what actually HPC can do, because it's in our computer, it's taking time. But maybe if we assign more CPU or more memory, mostly it is consuming the CPU. If we assign more CPU in the HPC, then it can do it more faster. সবার রান হচ্ছে? আচ্ছা আচ্ছা ভালো। You can see that it's maybe it's now finished or completed. You can see here the result. So it is saying that 416912 something reads. Out of these 100% were paired and 3.97% were aligned. It's normal because we used only 2 reads, right? It cannot map to the whole genome. I mean, it can map, but percentage is low. So overall alignment rate is 98.35%. Now we will see what it yielded. So ls, and we can see here that the E. coli.sam, the file is there, E. coli.sam. So these are the index file, and whichever have the FAI, it will take. Another thing you need to notice that when we put the file name for the index file, like in this here, in this command, we only wrote .fai. We did not wrote the .bt2 something, which was the suffix of it. We did not write. Just check here which files are there. Is there any file named FAI only? I mean, the fna.fai? There is no file. But when we write the index name in the command like this, we will just write the FAI, not the BT2, because it will automatically take those 6 files it generated for indexing. So do we all have the E. coli SAM now in our computer? It's not necessary. It depends on your genome file, genome sequence, and the chromosome it has. It will depend on that. Since we have something now, we can just check how does it look. So the E. coli.sam file looks like this. Have you all generated the SAM files? And now we can see it here. Is the sequence alignment mapping format. Again, lots of gibberish things. No, these are actually quality file. I think you can identify that these are the quality values, the quality score. These are the actual sequence. But what does the other things mean? You can remember that we stopped here, right? In our lecture, we stopped here the SAM or BAM file format. It has something like this kind of header. then the sequence, then the quality score. This is a smaller mapping file, but our one has longer sequences and longer mapping quality scores. So these are the read ID, the 1497 or the primary things. These are the read ID, then the read sequence, then the read position. For example, here we can see that chromosome 1, 497. It is the position of that read in the genome where it aligned. Here you can see that it's saying 37M. 37M means there are 37 matches. In this region, 37 matches are there. If we go into more details, মুখস্থ করতে হবে না, but you will need to have the idea that what it is saying. Okay. So there will be queue name or query name. The query is the read that we given as query, and our subject is the reference genome here. Flag, bitwise flag, pairing strand, mate strand, etc. So if it has a paired end read, another read, or mate pair read, it can have the flag. The R name here, query is the reads and the R name is the reference genome name. Position, one based leftmost position of clipped alignment. So where it is located in the genome, it can be found by the name position. There will be map queue. Map queue is the mapping quality, which is Fred scaled. Our quality score previously we saw for the first queue. It was also the Fred scaled, and map queue is also in there, that scale. Then there will be seizure, extended string operation. It says that if we go there, this thing that how many of these is aligned, it is shown there. MRNM, it's a mate reference name, M position, it's mate position. If it has a mate pair, then where is that it will be needed. So when we have the paired and read, we have the one read aligned in one position and the second read aligned to another position. So where is the second read? It will also be located. Then the insert size and query quality, etc. These information are available in our .sam file. So these can be a very good document for where it is aligning and about the mapping information. Maybe this is a more detailed version. The query name, which is red in color, you can find it here, the M01121 something. This one is a query name. In this case, the read file name. Then 2, the flag value, which is 163. And it says that whether it is another paired read or not. The reference sequence name, which is here, is chromosome M, maybe the mitochondria chromosome here. So CHRM is the chromosome position, location, and the position is 480. So chromosome AMR 480 base pair is the position. Then 60 is the Fred scaled mapping quality score. So how well it is mapped, it can be revealed by this mapping quality score, which is 60 here. The seizure string, which is for 148M2S. This means it's 148 times, it has matches there. equal sign, if there is an equal sign, which is this, it shows that the met reference matches the reference name. The position is 524. The insert size is 195 bases. And then this is the real sequence, that the read sequence, and this is the read quality that we had. The read has an additional optional field that accompany the MySeq analysis. So these things here, these can be some optional values which we can explore when we actually do the analysis. This one? Query sequence on the same strand as the reference. So it's actual the sequence, this sequence. Oh, okay. I think there is the same strand on the same strand as the reference query sequence. Okay. So SEQ plus minus কিছু একটা থাকতে পারে। Okay, I will check that and we'll let you know, but maybe there is something sign that I cannot remember right now that will tell you that whether it is in the same strand. For example, here they said that this information should let us know that whether it is in the same strand. Okay, so do we all have the .sam file now? And then we can proceed with the next step, which is so this is our file. These are the header information and the individual sequence information. Valid question. Okay, so our next task will be to convert it to BAM, to binary alignment format. So there is a very interesting tool which is called SAM tools. It can do anything. It has multi-purpose accessories. For example, SAM tools will help us to convert it from SAM to BAM. Also, it will help us to sort according to the indexed reference. It will sort the alignments. And then we will make another indexing for the BAM file. So what we are going to do now is converting the SAM to BAM and then order the aligned files and then make it ready for another indexing, which is the BAM index file. So try this with, at first see whether in your computer you have the SAM tools installed. You can just write SAM tools and see if it is there. If it is there, it will show the manual of that tool. Why do we need a BAM file? Any idea, anyone? SAM is also, is a good format. Actually, BAM file is easier for the computer to read because it is in binary format. It takes less amount of space and it is easier to transfer compared to the SAM. So they are trying to convert it to BAM file now. So if the SAM tool is not installed in your laptop, you can just write the same thing, the sudo apt SAM tools. If it is Ubuntu, then apt install SAM tools. If it is not, then you can download the SAM tools and run it from the, build it and then run it from the folder. So our next command will be to convert the SAM to BAM. And for that, we will just use the view option of the SAM tool. So you can see in the manual here also that the view, what does the view do? Commands, FADEX, something, mark to packet, merge, viewing. So it will just convert SAM to BAM. So just to convert SAM to BAM, we can use SAM tools, then space view, then space -BS. -BS it is meaning that it is telling the tool to convert the SAM file to BAM file. And we can keep the same name, that ecoli.bam. And try this and see what it yield. BS, it's for BAM view, binary view. S is for SAM, or -beta is for binary view. Okay, so in my computer, it's done and it's now generated the ecoli.bam file. Do you know how to check the size of the file? Whether the SAM file is bigger or the BAM file? We can try it, ls-lh. So the BAM file is 90 megabase pair, megabyte, and the SAM file is 324 megabytes. So you can see that it's a very compressed format and it's easier to transport. Try to see the BAM file. How does it look? You can just write less, LESS, then ecoli.bam. It's saying that it's a binary file. If I'm sure if I want to see it, I will put yes. And this is the binary file. Actually, it's not human readable, but this is actually the BAM file. And we do not need to read it. We have the information from the SAM file already, but it's for the computer for further analysis. Okay, so everyone could try convert the SAM to BAM, right? Then we will go for the sorting or making it in order. So SAM tools sort ecoli.bam. It's another interesting application that is sorting. So SAM tools, then space, then sort. We'll sort it. Then the BAM file. -O means output. In most of the tools, you will see that the -I refer to the input file, -O refer to the output file. So in -O, ecoli botai2 sorted. Make sure that while you name the file, you put something that indicates that what type of file it is. For example, now the file I am generating, it is sorted and by bow tie it is mapped. So I kept all those information there. In the output file, I named it as E. coli bow tie 2 sorted BAM. But not necessary that you will need to give this name, but this will make your life easier later so that you can identify that which files are sorted one, which file is not sorted one. And it's a good practice in any kind of informatics work that you keep your namings right so that it can be tracked. So SAMTools sort, then the BAM file, then the output file. I hope by now, while moving around the Linux environment, you are more used to with the concept and you are more finding it more user friendly, right? No? You can just give a space and then give the tab and then find the file. So what does it yield? It will yield a sorted BAM, which I will not dare to see again, but because this is also a binary file, but it will sort it according to the reference genome. So here we have the sorted BAM also now. If we try to see the properties of those files, we can see that the E. coli bow tie 2 sorted file is more less, I mean 63 MB only. Why we are doing this? Can anyone tell? I mean, after doing some analysis, it might came into our mind that why we are doing this. We are trying to map our read with the reference genome, right? The two reads we had. So at first we did the SAM alignment, which is a human readable format sequence alignment map. Then we build the BAM alignment, which is a binary alignment format. And now we are sorting it out, and the final goal of this is indexing the bow tie sorted BAM, because for making an index we need to sort it first. So we had this reference genome earlier, and you can remember that we indexed the reference genome earlier with the bow tie 2. The tool was bow tie 2 index, then the reference genome name, right? Only blank faces. Bow tie 2, BT2, yeah. So now we are going to index this with the SAMTools for this BAM. So SAMTools, then FADEX, then the actual E. coli something, that FNA file that we had, we will generate the index file from here, and you can see that. Oh, sorry, it could yield an FAI file, which was not present there earlier. From BT2, it was not, there was no FAI file. But here now we have a FAI file for SAMTools. And the last step is to index this accordingly from, we just indexed the genome reference genome file again with SAMTool, not with bow tie. When we did it with bow tie, we had the extension files named BT2. Okay, so now we are doing it with SAMTool, FADEX, FAI. This is called that do the indexing in FAI format. So FAI FASTA index, DX, indexing format. Then the GCF, the reference genome file. And when you run it, you will get this file. You will get this file, which is .fna.fai. But earlier you got the BT2 files only. And lastly, we will do the SAMTools index E. coli BOTI2 sorted, the one for indexing. So SAMTools, then space index, the sorted file. And now see that what we got. We got the E. coli BOTI2 sorted bam.bai. It's a BAM index file. This is BAI. The other one was FASTA index file. That's why it was FAI. But this is the indexing command. Why do we need the indexing? I hope all of you are understanding that why we are indexing the file first. Because this is a whole genome is a big data, right? So where the location is, we need to sort this according to the chromosome, according to the position. And the BOTI, SAMTools, these tools can index the files. Do you have IGV installed? IGV is Integrated Genome Viewer. So whatever we were doing now, till now, was in the terminal. It's a command line format, but it might be better if we see the alignment ourselves, I mean, in the graphical format. So there is an option, we can use the IGV. Also, we can use another tool. Say you are in a remote PC and you do not have the graphical option, then you can do it with T-View, right? Something there is called T-View. So this one can be also viewed in T-View. So let's first check it with T-View, SAMTools, then a space, then T-View, then show it the BAM file. So the E. coli sorted BAM. So it will show me something like this, where I am seeing only the N, then the aligned files here. So here we can see that the read sequence where it is aligned. And if we just press the right arrow button or the left arrow button, then we can scroll through the whole sequences and we can have the idea that which the sequences are mapped into which area or which position. Okay, so it's not, I mean, it's just to have the idea that where it is. Also, we can see it using IGV. If you have the IGV already installed, then you can just open another terminal, not this one. You can just open another terminal and write IGV and then press enter. So IGV actually works with in a Java for interface. So it will open a Java interface graphical software. So something like this. It's called Integrated Genome Viewer. It is very helpful in some times. I mean, if some minor, if in some basic analysis, it can, in-depth analysis, it can help us. So if you have this interface open, you will need to show it the genome you are going to use. So for that, you can just click on genomes. Then you can write that load genome from file. Since we have the bacteria, E. coli bacteria genome with us, we will put it as a reference genome here and load the genome from file. And then where is it? The GCF file. It's in the mapping folder. And we can just show the GCF FNA file, this one. This is the actual genome file. And if it is loaded, you can see that here it is showing 2 chromosomes. I think one is the chromosome, another is plasmid. And you can just zoom in to see more about this. Anyway, it will not show right now. When we will put some BAM file here, it will be more relatable. So could we all load the genome in the IGV? Try it, try to load the genome, then we will proceed with the later part. So for those who has completed so far, you can try with opening the BAM file from here, like file, then load from file. And then open the sorted BAM, E. coli bowtie 2 sorted BAM. And you can see that it will come like this here. In some point we can see some I, right? Here it is written as I. I means that there is an insertion, which is not in the reference genome. And if we if it is not coming like this in your computer, then try to zoom in. The more you zoom in, it will show you the sequence here also. Like this. So IGV is helpful in showing you that where is the reads actually aligned. And whether there is enough read or not, something like that. So this is what we got from the alignment, the SAM and BAM file. And we can visually, we can visualize this here. And if you just hover your mouse there, you can see that it is saying that it is the reference span in which chromosome. Then the how many reads are matched there, like 150M means 150 match are there. Then the insert size, read length, read name, exact location, pair orientation, forward 1 R2, F1 but R2, মানে দুই উল্টা দিকে ম্যাচ। IGV, acha, IGV, the BAM file, the sorted BAM. You will open the, at first you will load the genome from the genome, then load genome from file, then show it the genome file in the mapping folder. The genome file is GCF something FNA. And after loading the genome, you will load the BAM file. So file, then load from file. First genome sequence je file ta seta load hobe. .fna, jeta the reference genome. So genome, then load genome from file. Then you will find it in the mapping folder. And here you will see that GCF something genomic.fna, this one. So for human genome or Arabidopsis or mouse genome, IGV has already built in some genome, but these are not very common, like E. coli genome is not there. So when you get used to with this, specifically if you get used to with the IGV, you can have many more information, many more interpretation actually. So try checking the options it is showing. For example, what it is giving here, or in the try zooming it out, then also see what it is happening, what is happening here. So in this way, you will understand the alignment format more. So for loading the sequence, you have to do the, you have to load the genome first, and then you will have to load the file. From here, the E. coli bowtie sorted BAM file, the .bam file. Which one? Loading. Okay, at first the genome, then load genome from file. Then you locate the genome. It's in the mapping folder, as far as I know. Mapping folder, you will find the GCF something .fna. And just open it. So, oh, okay. So one thing you can just go to the chromosomes here showing, not in the all, you can just go to chromosome 1 and then load your BAM file, load from file. Then the E. coli sorted BAM, then open. And it is saying that zoom in to see the cover. So let's zoom in. And when I do the zoom in, then it comes like this. And I can zoom in more to see the, even in the sequence level. And you can see that on the upper panel, it is showing the base pair, the location of the genome. And the distribution here, you can see it is coverage, and how much is covered. You can see something here. If you, I just wanted to, note that for this blue one, it is showing the orientation as R1, R2. So that means the both of the read are in same orientation, in the reverse orientation. And for the red one, it is showing F2R1. I mean, it is the forward in the second read is in forward 5 to 3, and the other one is in 3 to 5 position. Okay, so everyone could use the IGV, right? IGV is easy to use. File name. Oh, এটা actually বড় হয় না. The name is E. coli bowtie2 sorted.bam. So for those who could not open the file, it is in the file, then load from file, and in the mapping folder, you could see the E. coli bowtie2 sorted file, right? E. coli bowtie2 sorted file, this one. You will need to open this BAM file. You can open any BAM file actually if you have the right reference genome, and you can see it in the IGV. And see, when I open two files, you can open two files simultaneously and make a comparison between the two. So this is also a BAM file. This one is also a BAM file, and you can make a comparison. If we need to do comparison, then we can open it in 2-track and then see how does it look. I mean, where is the variation? So for us, these are actually the same file, so it will not problematic. Okay, so the last command that we will deal with before the lunch, which is the depth calculation. So we can actually calculate the depth of the alignment we used. It's a bit complex command for some of you. It says SAMTools depth SAMTools depth, then the BAM file name. If we want to see how is the depth, then just enter it, and you can see that it will show the chromosome name here, the position, and the depth. But it is a never-ending file. I mean, it will end later. So let's give it a Control-C. If you want to cancel any job in Unix, you just press Control-C. So what I was trying to gather the information about depth. So let's do some bash scripting here, and there you will understand that why the scriptings are necessary for us to retrieve data. So here from that file, the depth was calculated. I mean, the list of depth file was generated. Then this sign, the pipe sign, it is used for taking the output from the previous command and feeding the next command with that output. I mean, for the next command, this output file will be used as the input. So keeping it in our pipeline. So the first command, then I will use the pipe sign, and then there is another command which is a bash command, and which will actually do the calculation. Here it is saying that take the summation of third column. So this is the third column, and take the summation, then make an average and divide the average from the summation with the number of reads from the summation. Anyway, this is just an statistical scripting that will give you some statistics about the depth of the alignment. And if we enter it, we will see that it's 20.5628. Since we actually use only 2 reads, it should not be that much depth. So it came out as 20.5628. So in any case, for assembly or alignment file, we can calculate the statistics actually, and that will give us the idea that whether our assembly or alignment this is good enough to go to the downstream analysis. Okay. So are we all in the same page now? No? So we are trying to align our 2 reads with the reference genome. So align means we are trying to map. So this is a reference mapping. Since we have the reference genome, we want to see that in which position these 2 reads actually map. And we need this. I mean, it's kind of, if you have a reference genome and you have a new species sequence, and there you have the reads, then you can align those reads and see whether there is variation. We will go to that later, but you can see here if we find something like this is an insertion maybe here, which is not present in the reference genome, but is present in the our read. So that's how we can compare the genome later. But so far, we just did the first QC, that the quality assessment. Then we trimmed our sequences accordingly, according to the threshold level. And then we use those reads to map to the reference genome and see how it comes. But this is the major portion of most of the genomic analysis we need to do. And if you understand it, you will we'll get things easily later also. Okay. So do we want a lunch break now? Okay. Okay, yeah. Okay, this is the actual read map here. If you just zoom in more, these are the different part. I mean, these are all the reads, and where there is something difference. So in this read, there is something different. That's why it's colored. But this is actually like the reference genome. So that's the ash part. Okay. So is there any question? No. Okay. Thank you.
So we are going to meet tomorrow right after lunch, like after having lunch. So maybe it's better that we actually or whatever. to the board in that.
Oh, yeah. So if you need to leave things there, we can arrange for things. I'll ask for the details. And the other thing is there is a self-guided Chimera X tutorial that we posted on the channel. So if you get time, go through it, because in tomorrow's lecture, you don't need to understand the full part, but we'll use AlphaFold through Chimera X. It will help you in the morning session. So, just go through it whenever you can. And what we are going to do tomorrow is the first part is AlphaFold, but the second part is whatever the MD part you couldn't catch up, we will catch up with the MD part. So that's why if you go through that tutorial as much as you can, the Chimera X tutorial, it will be easier for tomorrow to get through it.
Also, I have uploaded a file for the remaining part of yesterday's task. So if you follow and submit those files as instructed, you will get a trajectory file that is .dct files. You may be need for the analysis, MD analysis for tomorrow's session.
Well, actually, if you download the files before you go to the board, we can do the analysis on the board itself. So, yeah. Okay, so 2:30, you'll be back here at 2:30.